Okay, so here we're using Stirling's approximation to approximate as limit n tends to infinity 1 over n times log of n choose np. Right, and we'll end up seeing that this actually goes to and equals the as n tends to infinity, it equals the same thing as we saw in part 1 and 2, which is the binary entropy function. So this is equal to limit. So I'm going to say limit n tends to infinity here, but I'm going to assume that it's going to be the same throughout. So I'm going to put ditto signs. 1 over n factorial divided by n minus np factorial times np factorial, which is equal to, what is Stirling's approximation for n factorial? It's 2 pi root n times n over e to the e divided by 2 pi root n minus np over e to the e. Wait, not e, sorry. It's to the n. What am I doing? To the n minus np times root 2 pi np over e to the np. So log of this. That's why. Like, why are things getting cancelled so easily? It's not the case. So it's log of that, right? We have a 2 pi and a 2 pi get cancelled. We have an n and an n here which get cancelled, which is equal to 1 over n log of. So we see that we have an e to the 1 over e to the n in the numerator, and we have 1 over e to the n minus np, and we have 1 over e to the np in the denominator. So totally in the denominator we have another 1 over e to the n, and in the numerator we have a 1 over e to the n. So the e's on the numerator and the denominator get cancelled, right? So I'm going to simplify this and write this as 1 over root 2 pi, and let's pull the n out of this. So we have n times 1 minus p. I'm going to write the 1 minus p separately. 1 over root n. And let's see. Then we have n to the n divided by n minus np to the n minus np times np to the np, which is equal to ditto again log of 1 over root 2 pi 1 minus p. That looks ugly. Root 2 pi 1 minus p times 1 over root n times n to the n. Now let's pull the n out of this. So we have n times 1 minus p whole to the n minus np times n times p np. Alright, so we're almost there. Same thing. I'm going to take a negative 1 out and say this is log of root 2 pi times 1 minus p negative 1 over n log of root n. Now I'm going to keep the remainder as plus log. Right, okay, so now how do we break this up a little further? So let's just actually pull the n completely out. If we pull the n completely out, we get n to the n divided by n to the n minus np, and if we pull the n out from here, we get n to the np, right, times 1 minus p to the n times 1 minus p times p to the np. That's what we get. Now this term here, n to the n and n to the n minus np times n to the np, these get cancelled because they're both equal to n to the n. Right? So let's do this again. 1 over n times log of root 2 pi, forgot to close that bracket there, 2 pi times 1 minus p minus 1 over, I'm just going to pull the 2 out of this, because, or rather half out of this, because log of root n is equal to half of log n minus, now log of 1 over n 1 minus p to the n times 1 minus p times, what I'm going to do now is I'm going to actually take that n out, right? So we have 1 minus p to the 1 minus p times p to the p, this whole to the n, right? I'm just going to pull the n and the exponent out because it's the common exponent for both. So I'm going to pull it out, and we have 1 minus p to the 1 minus p times p to the p to the n. Now when we have this, n will come out in the log, right? Because log of a to the x is going to be x log a. That's exactly what I used to pull out the half here. So when the n comes out, you know that it's going to get cancelled with the 1 over n, so I'm just going to cancel it right away, right? So now let me actually, since we have no n in this expression, we only have log of something. Now let me actually apply the limit, right? I'm going to write limit n tends to infinity, so we have one step where it's there. And now when I apply the limit, what happens? So this, whatever is inside here, is just a constant. So when we have 1 over n which tends to infinity times log of a constant, this log of a constant is just going to go to 0, right? So this is going to go to 0. And now we have 1 log n divided by 2n. But we know that exponentially, n beats log n, as in n is much bigger than log n. N is actually an exponentially larger than log n. So as n tends to infinity, log n over n will go to 0 too. That goes to 0. So all we're left with is this expression which has no n in it, which is just negative log of 1 minus p to the 1 minus p minus log of p to the p. Pulling those out, as in using the properties of logs again, we have negative 1 minus p. I'm going to rearrange the terms. So we have p log p plus 1 minus p log 1 minus p. And if you look at this, this is again equal to h of p. Intuitively, why do part 2 and part 3 look the same? So part 1 is taking negative log of probability of some sample point, not some sample point, but what the probability of the random variables being themselves tends to, right? So this is not taking some particular values of the random variable into account, but rather the random variables themselves. So over here we saw that this is equal to log of p to the n0 times 1 minus p to the 1 over 2. What did I write? 1 over 2. It's 1 over n. 1 over n. P to the n minus n0. Right? So this, when you pull the n inside, divided by n. So these fractions themselves go closer and closer to the actual fractions p and 1 minus p. So what is this actually with the 1 over n outside? This goes closer and closer to the probability of the most expected sample point as n tends to infinity. So this term with the 1 over n outside is 1 over n log of probability of most expected sample point, because n0 would tend to something which is representing the fraction of ones, and the true fraction of ones, and n minus n0 would obviously represent the number of zeros. So what part 2 was talking about was the probability of the most expected sample point as n tends to infinity. What is this part talking about? It talks about n choose np, right? 1 over n log of n choose np. If you take a negative sign over here, as in we're trying to see why these two are equal. So if we make this positive and this negative, it should come out, these two should be still equal, right? So let's pull the negative sign inside, which is 1 over n log of 1 over n choose np. So what is 1 over n choose np? What is n choose np to begin with? You're choosing a fraction p of all the n. You're finding the different ways of choosing a fraction p of all the n items, or all the n ones. But p is the true fraction, or rather it's the most expected fraction of ones which you're going to see. So you're basically choosing the expected fraction of ones. So as n tends to infinity, what you're doing is you're basically choosing, you're finding the different ways in which the true or the most expected sample occurs. And 1 over that is just basically the probability of each of those samples occurring, right? So this term here is just basically within the most expected sample points. It's just the probability of any one of the sample points occurring. And as n tends to infinity, this sample point becomes much more likely than all the others, or at least you're going to expect the fraction of ones to be much closer to p than any other value. And as n tends to infinity, it gets closer and closer to this value. And therefore 1 over p is actually a good estimate of what the fraction of the probability of any given sample point which you're expecting to see will occur. And this is just the probability of that with 1 over n outside. This is just the probability of those sample points, and this is 1 over the number. So that's why these are approximately, that's why you can see that these two actually have an intimate relation, where this is the probability and this is 1 over the number of most likely sample points. Alright, so that's it for part 3 of question 3.